So this is if the out of band portion of the spectrum is there and there is some guard band, you need not to worry about it. You may let the sampling alias this part, but it must not affect this part. If it is aliasing this part, you don't mind, because you know this can always be. So this brings us to changing the sampling rate digitally, and the motivation is, as I mentioned earlier as well, that let's say you are sampling a signal which is at 70 megahertz. Okay, this is at 70 megahertz. The bandwidth is, for example, 4 megahertz, but this part of the spectrum is not clean. Okay, so you have passed it through an analog low pass filter, something like this, which has given you the entire spectrum till 72 megahertz, minus 72 to 72 megahertz, but the part of the spectrum is not clean. If this is the case, then you don't use band pass sampling, because this spectrum is not clean, but rest of the spectrum is clean. So it's better that you sample it at what rate? 1. So this is 72. By the way, 70 megahertz is the standard IF. It is used almost in all digital receivers, 70 megahertz or 21.4 megahertz. So you sample it at 144 megahertz. Once you sample it at 144 megahertz, this is what you get. So you get this here, and all this noise here, and then copies of it. So at 144 megahertz, you will get a copy, and this is your half the sampling frequency. So this will corresponds to minus pi to pi, and these are the copies, right? So minus pi to pi, you get this, and these are the copies. At every 2 pi you are going to get a copy, and minus 2 pi you are going to get a copy. We know this, right? Okay, now what is usually done is that you remove this noise and bring the signal at baseband. Okay, so you bring the signal at baseband, whereas the pi, you can simply say that the pi still corresponds to half the sampling frequency, which is pi corresponds to 72 megahertz. Pi still corresponds to 72 megahertz. So if 72 megahertz corresponds to pi, then, or pi corresponds to 72 megahertz, then 1 corresponds to 72 over pi, and you can figure out, sorry, it will go like this, pi over 72 into 2 megahertz. So you can exactly figure out what corresponds to this frequency digitally, and this is pi over 36. So this is pi over 36 to minus pi over 36. This is your spectrum. Okay, pi over 36 and minus pi over 36, or this is 2 and corresponds to 2 megahertz and minus 2 megahertz. Now remember that though once you bring the spectrum here at the baseband, at this point we really are not focusing how you bring this, but we can bring it down by multiplying it with an exponential shift in frequency. So you bring it here, and once you bring it here, the signal has been sampled at 144 megahertz, and you really only require how many mega samples? 4 mega samples per second. So you are keeping a lot more samples than what is required. Okay? And this requires that once you do this operation, you must throw away redundant sample. As soon as you get this, the very first thing you must do is that throw away samples. Must. So this is really what is done, that you say, okay, 144 megahertz, and because you don't need these many samples, so if you divide it by 4, 36. So you are going to, 36 so you are going to, 36 so you are going to 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 downsample it by 36. And 36 means you keep one sample and throw away 36 samples. So you can reduce the cost of the system by 36 times by throwing away samples. Why? Because all these samples are not required. These samples are not required because this is equivalent to saying that you have a sinusoid and you have around 37 samples, okay, where you only need 2, or 70 something samples whereas you only need 2. So for this reason, that whenever in signal processing you are cleaning the spectrum, after cleaning the spectrum or moving the spectrum up and down, that after you move the spectrum you have to upsample it, or before you intend to move it up you need to upsample it. Either so in this case where you are moving the spectrum down, you always downsample it. It is shown with this arrowhead. And whenever you move it up, because in the transmitter you need to take the spectrum, move it up. If you move it up, you always first need to move the number of samples up, and then you have to mix it with an exponential. So these two operations are done in a communication receiver, and this operation where you are throwing away sample is called downsampling, and where you are adding more samples is called upsampling. Let me give you a reason why you need to do the upsampling. Example is, let's say you have this signal at baseband at 2 megahertz video. So you digitize a video and the video is at 2 megahertz. It's a 2 megahertz video which you sample at 4 megahertz. Okay, and now you need to throw this video on an A to D converter at 70 megahertz. So you need to move it up. How you move it up? To move this up, you need to multiply it with the cosine of 2 pi f naught t, or its equivalent digital form, which is cosine of omega n or omega naught n. Okay, this is what you need to do. If you are doing it digitally, usually we do it digitally, so you need to mix it with a cosine which corresponds to a 70 megahertz cosine. And we know how to get a 70 megahertz cosine. At what sampling rate you can create a 70 megahertz cosine? How many? 140. At least you need to have 140 mega samples per second to generate such a cosine. Okay. If you are doing it digitally, in every second you must have 140 mega samples. Okay. This is your digital signal, which is your video. So you have a video in. This is your A to D converter, and here out of the A to D you have only 4 mega samples per second. Okay, 4 mega samples per second. The issue is, you remember in signal processing we have learned that you multiply on sample by sample basis. Once you are multiplying two signals, got to be on sample by sample basis. So the only way for you to multiply this signal with this signal, if it is done digitally, its sampling rate, both the sampling rate must be same. Okay, both the sampling rate must be same. If you are mixing a 4 mega samples, if you intend to mix a 4 mega sample with 140 mega samples, okay, you really need to bring it up to 140 mega samples. Rather, you bring it up even more, because your highest frequency, if once you mix it, is going to be 72. So that's the reason, instead of this at 140 mega sample, preferably make it 144 mega samples and bring it up to 144 mega samples. So you bring this signal up, and only then you can digitally mix. So this is the only way you can digitally mix, that you bring it up, and then you mix them together at the same sampling rate. Then you throw it on an A to D converter. So generating this is very simple. All you have to do is generate +1, -1, +1, -1, +1. This is really how you generate it. I mean, you need not to compute cosine. If you are just generating this, you say plus, minus, plus, minus, plus, minus. You can generate at 140 mega samples per second. You can do it like this. So you can just figure out a way to generate this. Then you mix it, and after you mix it, then you throw it onto a D to A converter. So this is where you have to upsample it. So knowing this,
upsample हमें इसको भी चेंज करना पड़ेगा 4 में से 7% को प्लस में मल्टीप्लाई विद कोसाइन.
Yes, to multiply it with cosine you have to bring it up. Otherwise you will not able to do it.
When we convert it from 4 megasamples to 144 megasamples, what does that mean?
Okay, now this is a good question. What does that mean? Okay, so it means that if it simply means that between two samples, let's say if this is your original samples, okay, these are your original samples, it means that you have to add 36 more samples between these two samples, 36 more samples to bring it up, okay, and you have to add it so that the original shape of, though these are redundant samples, but you have to interpolate to put these, how many depends, so all these samples between two samples. So this is what is meant by bringing it up, that you have to insert so many samples to bring the sampling rate up. Okay? So obviously you have to use some algorithm to do that. There is a simple way is that you insert zeros, obviously that will change the shape of the signal. The other one is you stretch a straight line, this is a linear interpolator, and you add samples. Obviously this is also not correct because you know this is not a straight line. You need to figure out a way to still keep the shape of the signal as is, and we know the ideal interpolator is a sink, which is a low pass. We'll see a sink, if you put a sink here, a sink here, sink will give you an ideal interpolation. It will give you a very nice interpolated curve. But this is the redundant work you are doing, not because it is required, but because you are mixing it with the signal which is at higher frequency. So in order to translate it in frequency, you got to do this, and this requires a change in sampling rate, a lot of extra work which you have to do. Usually you will find that many companies offer this digital up and down converter. They have this chip which you can get from TI, from Qualcomm, from analog devices, from almost every vendor provides this, because it is such an integral part of anything you do in communication. This is an integral part, that a digital up and down converter does this, that it will offer that you can up convert a signal at, they'll offer big numbers, that 2000 sometimes you will able to up convert, and similarly they will offer big numbers for bringing a signal down. They also provide you with cosines and sine for mixing, because they'll say you can have so many cosine and sines where you can mix, and you can systematically downsample and upsample. So let us see what is involved in bringing sampling rate down and up. And we know the motivation. The motivation is that you got to do it, because if you don't do it, this is at the front end of a receiver. If you don't do it, you have more number of samples than what is required, so your whole receiver will be very expensive. So you do this so that you can reduce the cost of your receiver. So this background, the need to change sampling rate is, and this is what is called the multi-rate signal processing. You do decimation, you do interpolation, and changing sampling rate, and sometimes you have to change it by non-integer factor. We'll see how this is done. And oversampling sometimes eases anti-aliasing filtering. I've already told you that sometimes, though it is not required to sample at high rate, but you have some noise here, some noise here. So to avoid aliasing, you sample at high rate and then digitally clean the signal, and then you bring the signal down. In image processing, there are altogether different reasons for downsampling. In image processing and even in video processing, you have a frame. A frame is first passed through a low pass filter. A low pass filter means you throw half of the frequencies and you have an image which has only no frequency greater than pi by 2. in x direction and no frequency greater than pi by 2 in y direction. So you pass it, we call this a half band filter. In image processing and video processing, especially for compression, you pass it, I'll show you an example, low pass filter, and you pass it through high pass filter where you have no frequencies less than pi by 2 in any direction. Okay, so once you have this, you know there is a redundant sample after every sample because of that highest frequency must be pi, but now it is pi by 2. Okay, so you throw away every other sample. Once you throw away every other sample in x direction, every other sample in y direction, the image size is reduced to 1/4. Okay, so this is what is done in image, and then you take this and again pass it through low pass filter. Okay, again you throw away sample, again you pass it through low pass, and you keep doing this until you get a pixel, which is the most important pixel in your image, which is low. Okay, and if you follow, so you are passing it a low, and then again you do a low, then again you do a low, and this, it depends that at how many levels you want to do the decimation, and then this is the important leg of your image. Okay, this is the important leg because low frequencies, but then you have some low, high, low, high, and here you have high frequency contents. You pay a special focus to encode this part, and you less focus to encode this part. Okay, and this is what is done, and I'll show you an example of an image which has gone through this process. But this topic will also help you to understand these techniques, especially wavelet transforms are used to for filtering purposes. But so sampling rate conversion is equivalent to thinking about this is really equivalent to as if you convert a signal to a digital signal. Then let's say here the sampling rate is 4 megahertz. So you convert it, and now let's say you want to resample it at 8 megahertz. It is equivalent to converting this digital signal back to analog, and then this analog filter back to digital using T dash sampling rate, for example 8 megahertz. So mathematically the process is equivalent to passing a signal through a D to A converter and then again to an A to D converter. For example, I gave you an example where I said, okay, you have a spectrum here, and this spectrum is at 70 megahertz and 4 mega spectrum, so you sample it 144 megahertz. Then you clean it up. After cleaning it up, you have this spectrum, but the sampling rate is still 144 megahertz. Now you know that you can easily sample it at 4 megahertz. So what you do is you pass it through a D to A converter at this rate, 144 megahertz. Okay, so again convert it to a continuous time signal, and then again now you resample it at 4 mega. You can always do this, right? But that will involve an extra D to A and A to D converter. If you do this, that first you do some processing, clean the spectrum, bring the spectrum down, then you say, okay, now I think I have more samples than what is required, so why should not I convert the signal back to analog and then use an appropriate sampling rate to convert it back to digital. So but that will require 2 of these devices, and these devices are expensive. Okay, so this is the reason that you learn these techniques, that to avoid putting these devices you do this digitally. So doing this whole thing digitally is that you still somehow manage to reduce the sampling rate or increase the sampling rate by digital means. So this is the motivation of these techniques. So here is an example. Let's say you sample a signal at, this is a 2 megahertz, for example, a 2 megahertz signal. Okay, and you sample it instead of 4, you sample it at 8 megahertz. Okay, a signal which is sampled instead of 4 megahertz, you for some reason you sample it at 8 megahertz, and you know the process at this is your sampling rates 2 pi over capital T, 2 pi over minus 2 pi over capital T. To make copies of this here, and this is 1 over T, and then you change it to digital, this multiplied by T, so you get this at 2 pi, this at pi, and this will be at pi by 2. If in this particular example this is pi by 2 minus pi by 2 minus pi and like that. And now you throw every other sample to bring the sampling rate back to 4 megahertz. Okay? So 2 megahertz sample at 8 megahertz will give you this. Let's say if you sample 2 megahertz at 4 megahertz, what will you get? Sampling 2 megahertz at 4 megahertz will give you this. The copies will be where? Right here, right? ठीक है ना? If you are sampling a 2 megahertz signal at 4 megahertz, this is what you will get, not this. Am I right? Okay, so this is what you get. So this is equivalent to the digital part. This is 1 over T, and 1 over T in this case is 8 mega. Oh, sorry, 4 mega. In this case, 1 over T is 8 mega. Okay, in this case, sampling frequency is still going to be 2 pi and minus 2 pi, we know. But what about this? This is going to be at pi, and this going to be minus pi, right? So if you are sampling appropriately, your highest frequency will always map at pi and minus pi, always. So this is where you are not spending any extra sample to capture a signal, minus pi and pi. The spectrum will spread to minus pi and pi. If you are doing more than what is required, you will find some space here, as is shown in this case. So the important thing is that once you throw away samples, your digital spectrum, which is this, will again map to this. This is guaranteed. That if you throw away a sample, the digital spectrum will change from this to this because they are equivalent, mathematically equivalent. So throwing away a sample means two things. One is this 8 mega will be divided by 2. The other one is this frequency axis will be multiplied by 2. Let me redraw this. So it is equivalent to, so this is what you have. So I'm saying it is equivalent to, you divide this 1 over T by 2. 1 over T is 8 divided by 2 will become 4 mega. This is at pi by 2 and this is at minus pi by 2. You in fact multiply this by 2 and 2. But what will happen to 2 pi? 2 pi will go to 4 pi, and what will happen at minus 2 pi? Will go to minus 4 pi. Then there will be another shifted version of the spectrum which will come here at 2 pi. So once you throw away samples, the throwing away samples is equivalent to dividing the magnitude by those many samples, the at rate at which you are decimating. If you are throwing away every other sample, it is decimation by 2. You are multiplying your frequency axis by that factor and then making extra copies of the spectrum to make it look like this. It is really, this is what a decimation is all about mathematically, and it is shown here. Okay, this is what the decimation is all about. That if you decimate it by 2, mathematically your magnitude, this will be divided by m. Okay, so it'll make 8 mega go to 4 mega, so you are fine. Then it is this frequency, which is equivalent to pi by 2, is multiplied by 2, will make this pi by 2 go to pi and minus pi by 2 go to minus pi. So it is this is shown here. It is x exponential j omega over 2. This is how they are equivalent. For example, I'm saying the omega, for example, you have y is equal to x. What is y is equal to x? Y is equal to, at 1 you have 1. What is y is equal to x over 2? At now 2 you will have 1. So this is the expansion. Once you say y is equal to x is changed to y is equal to x over 2, it means the x-axis is multiplied by 2. This is a simple relationship. So mathematically you write x exponential j omega over 2. So but this will take 2 pi to 4 pi and minus 2 pi to minus 4 pi. So you have another copy which comes at 2 pi and minus 2 pi. This is the omega minus 2 pi over 2. Okay, so this is an extra copy of the spectrum everywhere, which will come at 2 pi and minus 2 pi and 6 pi and minus 6 pi. And there is a mathematical proof of this expression. I'll not get into that, but this is what is meant if you throw away every other sample or decimate it by 2. If you decimate it by 3, it will be divided by 3. Here it will be divided by 3. You will have 3 of these. You will have 3 of these. If you have 4, it will 4 of these. If you do 5, it will have 5 of these. So this is, but the important point is you can quickly come up with the answer, assuming that you have originally sampled this signal at 4 megahertz. Draw this. So whatever you get here will be equivalent to this, that originally if you assume that you have actually sampled it at 4 megahertz, you can quickly come up with the answer, that this is the answer. If not, then you go through these steps. Or another way of looking at it is that you take this, keep this as is, but take this multiplied by the axis by 2, and I'll tell you that what has happened. Interesting is, if you have strange looking spectrum, you really need to figure out what will happen. Okay, so if something like this, you need throw away sample. If you are throwing away more than what is required, then what will happen? Aliasing, right? If you throw away more than what is required, it will alias. For example, in this case, I say you downsample it by 4. Downsample it by 4 means you are sampling at, or downsample it by 4 means that you are sampling at 2 megahertz. And remember, if you sample this at 2 megahertz, you are going to corrupt everything. So, but what will you get if you sample it at 2 megahertz? You get this, right? This is what you get. And this one, this copy is at 2 pi. जी नमाज की ब्रेक कर लेते हैं. Somebody asked me to just do this. I'll quickly give you a hint, and that hint will be enough for you to solve these examples. It talks about precisely the MATLAB simulation I showed you, that if you undersample sine or cosine, what will happen. Okay. In this example, it assumes a cosine of 4000 pi t. It says xct is cosine of 4000 pi t. Okay. So this is example 4.1. So relating to example 4.1, 4.2, 4.3, it talks about a cosine of 4000 pi t, and the formula for, and remember, you just have to follow the steps. The steps are that whatever sampling frequency is given, you make copies of the spectrum at omega of s minus omega of s. So if you do that, it's the Fourier transform is pi delta omega minus omega naught, which in this case is 4000 pi t, pi of this and minus pi delta omega plus 4000 pi t. So this is the spectrum of a cosine. An impulse at omega naught and minus omega naught with magnitude pi. Okay. So the spectrum is this, and that's all you need to know really to do this correctly. So this is 4000 pi to minus 4000 pi. Okay. G? G plus, sorry. This is plus. So this is the spectrum, and if you are to sample it at, let's say in this example, you sample it at 12,000 pi. If you sample it in first case, let's say you sample at 12,000 pi. What do? At every 12,000 pi, you make copy of it at 12,000 pi and 12,000 pi. So it's simple. So let me draw this with another color pen. So it is the 12,000 pi. So going 4,000 here will be 8,000 or something like this. So similarly, and 4,000 here, here and here. Let me make sure it is in example 4.1. The sampling frequency is 12,000 pi. So at 12,000 pi, you go 4,000 on this side. If you go 4,000 on this side, it is 8,000 pi and 16,000 pi and 8,000 pi, and similarly you do this. And remember that half of it, which is 6,000 to minus 6,000 pi, corresponds to minus pi and pi. Okay? So you can actually know what this frequency, the digital frequency, is by remembering small omega is equal to capital omega into t. Using this simple formula will help you to exactly figure out what this frequency will map to. This frequency is 4,000 pi is omega, and this is 1 over t. This is omega s. Omega s is 2 pi over capital T. So you can compute capital T because 1 over t is omega s over 2 pi divided by 2 pi. So pi cancels out, 6,000. So t is 6,000. So you 1 over 6,000. So you divide it by that, and you will exactly able to figure out, and that will be 2 by 3 pi. So to say. Now it says that, let's say if instead of 12,000 I ask you to sample it at 6,000 pi, what will happen? Aliasing, right? If you sample the same at 6,000 pi, so from 6,000 you go 4,000 on this side. So if you do that, you will have a copy here, which is at 2,000 pi and minus 2,000 pi. This is what you are going to get. Okay? If you sample it at 0, you are still going to have a copy at 4,000 pi and minus 4,000 pi. But if you sample it at 6,000 pi, you get a copy here. And remember, 3,000 to minus 3,000 is your minus pi and pi. So this will go away, this will go away, you will be left with this frequency and this frequency. So a sinusoid, if not sampled fast enough, will map to another sinusoid of lower frequency, and lower frequency is equal to omega s minus omega naught. That is the relationship, and once you even reconstruct it, you will get a cosine, but it will be a slowly moving cosine. And again, it's simple that you draw this, then make copies, preferably on a tracing paper, make copies, just consider minus pi and pi, the rest throw away everything. That is your spectrum, the digital spectrum. If you are even going to convert it, you convert it, you get that. So coming back to what we are learning, okay, so here is an example where you throw away more samples than what is required. Right? So here is pi by 2 omega, and remember this is the formula where you are, the digital frequency is at every 2 pi over t. So following the same step which we have seen, that you make this, then make the sampling frequency, make copies of it, and ultimately you get this 1 over t, pi by 2, 2 pi minus 2 pi. And if I ask you to throw away, to downsample it by 3, downsampling it by 3 means keep one sample and then throw away 2 samples, keep one, throw out of 3, keep one, 3 samples keep one, 3 samples keep one. So use the same trick, pi by 2 multiplied by 3. Okay, we'll take this pi by 2 into 3 into 3 pi by 2, and similarly this will take this at minus 3 pi by 2. Okay, and anything which goes above pi and minus pi is very simple, will come back. Anything which goes above pi will come back an alias and will come back an alias. So because you are going to make a copy of this at 2 pi and minus 2 pi, or otherwise this 2 pi will go to 6 pi, and you are going to have exactly how many copies? 2 more copies of the spectrum. One at 2 pi and another one is at 4 pi. Okay, so this is the expression which says you are going to, this amplitude will be reduced by 1 over m, and you are going to have the frequency axis will be scaled by omega over m, and then you are going to have 3 original at 0, at 2 pi, at 4 pi. Okay, so copies of the spectrum, or there's the same thing copied here at 2 pi and minus 2 pi. But this is the example of aliasing, and this is true even if you don't, if you start from here and you say instead of 4, let's say 2 mega, and instead of sampling it at 4 mega, you first sample it at 8 megahertz, and then instead of doing 4, you divide it by 3, so 8 by 3, whatever it is. So you are sampling, in this case, sampling it at 8 by 3 megahertz, which is 2 point something, whatever that. So 2 point something. So you are sampling it at 8 by 3 megahertz. So you are not obeying the Nyquist sampling criteria, which says you sample at least 4 megahertz. So this is again this is what you are going to see. So this, if you do, obviously will corrupt your spectrum. If you do this, this obviously is going to corrupt your spectrum. So we must not do this. Okay, we must always make sure that this highest digital frequency, if you want to throw away samples, just one criteria, look at the highest digital frequency. The highest digital frequency must be less than pi over m, where m is the number which you intend to downsample. If you intend to downsample it by 2, the highest digital frequency must not be greater than pi over 2. Then you can throw away every other sample. If you want to throw away 2 samples, then the highest frequency must not be greater than pi by 3. Right? Because pi by 3 will then come to pi. So just look at this number. It goes 2 ways. One is, knowing the highest digital frequency, you can figure out the m, that how many samples can I easily throw away. This is one way, that you find out your digital spectrum and you say my highest digital frequency is not really greater than pi over 6. So you say it means I am keeping a lot more than what is required. The other way is, if I really intend to throw away samples, then I need to make sure that first I cut down my digital frequency to pi by m, in this case pi by 3. If really I want to do it for reasons, I first need to cut this down to pi by 3. I need to pass it through a low pass filter. Okay, cut the frequency spectrum which perhaps I don't require, which is out of band, some other band coming in my signal. First throw that away, and then you stretch. I mean, then you throw away samples. Throwing away samples means compression in time and expansion in frequency. It's an inverse relationship, always an inverse relationship. So this is a simple rule which says that if you want to do that, first use a pi over m filter, digital filter, pi over m, design it in MATLAB, pass it through this pi over m filter, cut what is not required, otherwise it will alias and corrupt this part of the spectrum, and now you downsample it by 3, right? And pi by 3 will go to pi. So this is a rule, that if you want to downsample, first make sure there is nothing beyond pi over m. If there is something beyond pi over m, you use a low pass filter to throw that spectrum away, pi over m spectrum away, and then you throw away samples to get to the spectrum. So this is important in decimation. So that otherwise doing decimation in time is simple, that you are keeping this sample and throwing away. This is decimation by 4. Out of 4 samples you keep 1. In MATLAB it is very simple, x, 1 and whatever, 3 to n. If you want to 1 1 means you are keeping, so 1 2 means you are keeping every other sample. 3 means you are keeping this, 4 means you are. So it's simple in MATLAB. A simple command will do the decimation for you, because decimation simply means throwing away samples. So throw away samples, and this is an example, and this is what will happen to your spectrum. If you throw away, depending upon how many you are throwing away, expansion, and this will be divided by, if you're doing it by 3, so this will be multiplied by 3, and the magnitude will be divided by 3. So this is what will happen to the spectrum, and you can easily experiment it in MATLAB. I'll show you MATLAB code which is doing this. Okay, so in MATLAB, if I decim, okay, so this is a wave file, and I'll successively throw away samples in this wave file. I'll show you the original spectrum, then I will downsample it by 2, okay, and then I'll show you the spectrum, then I'll again downsample it by 8, the original, I'll show you the spectrum, and I keep doing this, okay. You can use the same file, you can actually record your own voice and do the downsampling with that. DSP1. So this is the original voice. Look at the spectrum. So this is in time domain, and this is in frequency domain. Usually voice activity is here, and as you can see, the sampling frequency is around 11 kilohertz. So that's why you see pi here. It's a sample at 11 kilohertz, approximately 11 kilohertz. But you see most of the voice activity is only from 0 to even not at 2 kilohertz. Okay, most of the voice activity is here. So then what you do is you downsample. What you see here is a downsampled version where I'm throwing away every other sample. A downsampling means that the spectrum, though is shown on the same scale, but the spectrum will expand. So the spectrum will expand, and so it is really means that you cut it down from here and move it, but then I'm just changing the axis, but I'll show you on the original scale as well. I'll keep the scale as is, and I'll show you what is happening to the spectrum. I think it's just
welcome to DSP1.
Okay.
Welcome to DSP1.
So this is the decimated. Obviously the speech quality will degrade because there will be some aliasing, but this is a better representation. This is the original spectrum. Okay, once you decimate it by 2, so you cut it down and move it like this. So there is some aliasing here, but still the original voice activity is in this region. So though there is some aliasing, you will find some degradation in voice, but still acceptable perhaps. But remember, doing this, you have not passed it through filter. Ideally you must first pass it through filter. If you really want to do it, clean the spectrum, clean half of the spectrum, and then move so that this part should not go and corrupt this part. Okay, preferably you do this, but here I've not done that. I'm saying cut it down, throw away, and then again if you do this, what is meant by that? That you cut it down from here. G? There is. Yeah, there will be, because you are throwing away some voice components in voice. Usually these are important component, but even in a telephone exchange, the signals are sampled at 8 kilohertz. They throw away anything which is beyond 4 kilohertz. For example, if you listen to music on telephone, it is very bad because they throw away all high frequency content, but actually they filter it out, and then so in all exchanges, signal is being filtered out beyond 4 kilohertz, and then they digitize it. Okay, so this is, you cut it down, bring it up, you have this. Again, if you throw away, you cut it down and you shift it. So this is what you do if you are just simply decimating. But on the other hand, if you are, let me see if I can run that as well. That if you on the other hand doing the poly. Okay, here is the case where you actually no.
Welcome to DSP1. Welcome to DSP1. Welcome to DSP1. Welcome to DSP1.
So this is where actually in this file I have actually passed it through a filter. This is what is done. That before I decimate, first I clean it up. I say, okay, I really want to decimate for reasons that I don't want to support that higher sampling rate. Okay? So I use this filter, clean this part of the spectrum, and now cut it and move it. Okay? Though still I am corrupting, I am throwing away information, but I am not aliasing at all. So I cut it down and then I move. And then I again pass it through this filter and then I again move. So I keep doing this. The voice quality in this case will be much better than the voice quality in the other case, though I have the same number of samples end of the day. So this is what is done, and you can look at it. This is the voice sample. Yeah, this is the alias version of the signal. This is without polyphase decomposition, and this with polyphase decomposition. And here there is aliasing, but here there is no aliasing. And this is the primarily difference. Hardly. So the point is that if we are doing this, it is always preferred to clean the spectrum, as shown in the previous slide here. So if you really want to do it, first clean the spectrum and then throw away samples, decimation. So these are the rules. If you know there is nothing beyond pi over m, then you can throw away simply. Okay. So no aliasing if spectrum is 0 for omega greater than pi over m and pi. Nothing here, throw away samples. But if not, then pre-filtering is needed in digital domain. So you pass it through a pi over m filter and pass the signal and then throw away samples to get this. Okay, so this is if I show you the MATLAB code, this is what is done here. So I am designing a MATLAB filter of cutoff frequency pi over L or pi over M. So this is the filter I design using FIR1 command, and then I pass the signal through this filter first. So this is, you can use filter or convolution, you pass it through this, you have Y, and now you throw away samples. Throw away every other sample, okay, and to get to do the decimation. Okay, then comes the upsampling. Upsampling means that you have, as I explained earlier, you have these samples, and for reasons, okay, and I have already given you the reasons. Usually you are just adding redundant information. This is usually to mix it with a high sample signal. Usually this is the reason that you upsample, that you need to bring it up and then you mix and then you throw it out. So you upsample it, and upsampling requires adding lot more samples. All the circles are the added samples. So you want really to smooth the signal out. You don't want to change the spectrum of the signal. You want the spectrum to remain same. Okay, so that is the challenge. And this is how it is done, that first you add zeros. So sample 3 zeros, sample 3 zeros, sample. So every sample is replaced by 4 samples. This is upsampling by 4, that you add 3 extra zeros. And then you interpolate the zeros to bring these zeros to the actual values. So it is, upsampling is done in 2 steps. One, in first step you insert zeros, and in the second step you interpolate. You bring those zeros to appropriate values, interpolated values. And we already know that an ideal interpolator is a sinc function. In frequency domain it is a low pass filter. Okay, this is an ideal interpolator. And now you are going in reverse to what we did earlier. If I ask you, okay, this is a signal which is at 2 megahertz to minus 2 megahertz, and for example you sample it at 4 megahertz. So a signal sample at 4 megahertz will look like this. It is 4 megahertz, so 4 mega, which is equal to 1 over t. It is 0, it is, and this is what? 4 mega, right? And digitally, in digital domain, this will be, what will be the frequency where you're making copies? 2 pi and minus 2 pi. This is the digital signal if sampled at 4 megahertz. What if the signal is sampled at 8 megahertz? This is what an interpolation is. If signal is sampled at 8 megahertz, at least in frequency domain, it will look like this. It is 8 mega, right? And the next copy will be at, if it is sampled at 8, so it will be at 8, right? So this will be 4 mega. So this 8 mega will corresponds to what digital frequency? 2 pi, and this corresponds to pi, and this corresponds to pi by 2. So really this is what you want to do. In interpolation, you want this digital spectrum to change like this digital spectrum. Okay, this is what you do in interpolation, that the spectrum, digital spectrum, the pi here should be divided by whatever, divided by 2 or divided by 3 or divided by 4. But if you divide the whole axis by 2, so this 2 pi will also be divided by 2. Okay, or if you divided this by 3, this will be divided by 3. If you divide this by 4, this, so whole spectrum will be divided by 4. So you want to somehow apply a transformation, a digital transformation, which can change this spectrum like this. It is done in 2 steps by just inserting zeros. If you insert zeros in upsampling, if you insert zeros, and you can try this in MATLAB as well. Inserting zeros means simply dividing the spectrum, and this is what is shown here, that this spectrum should look like this spectrum. This is what you want in interpolation, that this 2 should go to 8 if you are interpolating it by 4. This pi should go to pi by 4. This is minus pi by 4 to pi by 4. The magnitude should be from 2 to 8. So you multiply, you want to multiply this by L. You want this to happen like this. So this should be changed like this. And it is done in 2 steps. First, let me tell you this. This is the first step. That after every sample, you insert 3 zeros if you are interpolating it by 4. If you do this in spectrum, if you look at the spectrum, you will find the entire axis will be divided by 4. Okay? And the amplitude will not change. So you will find pi will go to pi by 4. But the problem is 2 pi will be at pi by 2. And the 4 pi will be at pi. And similarly you will get extra copies, and always you get m minus 1 extra copies between 0 and 2 pi. So these are the extra copies. Inserting zeros, 3 zeros means 3 extra copies of the spectrum. Inserting 5 zeros means 5 extra copies. Inserting 1 zero means another extra copy. So this is what looks in. This is how it looks like in digital domain, in frequency domain, that inserting 0, take the frequency transform. You will find extra copies. Okay. So now you need an interpolator. An interpolator is a low pass filter. This is the filter. You want to bring the magnitude up by 4, so give it a gain of 4. Okay. So design a filter, multiply it by 4. And cutoff is at pi over L. So this pi over L filter will clean this in frequency domain, but in time domain this is a sink. The sink will give you an ideal interpolator. So let me show you what it is doing in time domain. In time domain you said this is a sample, then you have 0, 0 and 0, then this is a sample, then you have 0, 0 and 0, then you have this sample, you have 0, 0 and 0. Similarly you have these samples. Okay. The sink, what you are going to use basically is that once you use sink, will always pass through zeros after L samples, guaranteed. Okay, so the sink will be something like this. This will pass through this 0, then it will pass through this 0, then it will pass through this 0, and similarly if you have something here, it will pass through this 0. So this is a sink. Okay. So once you are convolving at this location will remain as is. I mean, this sample will not change values. Why? Because all these zeros will multiply with non-zero values, but this non-zero value will multiply 0 values. These zeros will multiply non-zero values. So this will remain intact. But once you shift this and bring it here, then what will happen? So then at this point the sink 0 will pass through this 0, right? And that 0, the next 0 will again pass through this 0, and this 0 will pass through this 0. So now the convolution will have contribution from all the samples. So this, you will multiply this with this. Remember in convolution what you do. So this is a sink, this sample multiplied by 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 this. So you add all of them together and you will find out it will nicely give you a value which will be closer to this one, because this has the maximum contribution. And as you move away, it will not change this value. It will never change these values. It will only add values here. And here the contribution will be more from this sample. And then less from this sample, very less from this sample, and less. And as you move up, less. But it will have contribution, so it will smooth out. I'll give you a very nice interpolation. A low pass filter will give you very nice interpolation. And this is what we do in for interpolation. This is what is being done. This is what is happening in frequency domain, and it tells you that all the things which you have added. क्या हो रहा है यार? Okay, but you can use the other type of interpolator as well, but they will not give you good interpolation. One is that you really do a straight line interpolator versus, okay, so the best is the ideal low pass filter. This is a linear interpolator, okay, that you just put a line and then you interpolate, but obviously the ideal interpolator is always better than the other kinds of interpolator. So this brings us to an interesting topic in signal processing which is called polyphase filtering. Let me first give you motivation of this. The motivation is in decimation, for example. In decimation, we say, okay, if you want to decimate, first you make sure that there is nothing beyond pi over m. So if this is pi, this is minus pi, and you want to do it pi over m, let's say m is 3. So if there is part of spectrum beyond pi over m, you need to pass it through a pi over m filter. So the first thing you do while decimating a signal is you pass it through a pi over m filter, okay, and then you throw away sample. Out of m samples you keep one sample, not any sample but keep one and throw away m minus 1, keep one, throw away m minus 1, okay. There is a problem in this approach, and what is that problem? The problem means that you are really doing something extra. And what is extra? That you are actually computing samples which ultimately you are going to throw away. Obviously you let's say m is 36, so you compute 36 samples, then only keep one out of those 36, throw away 35. Obvious question is that why should I compute what I am going to throw away? I should not compute that. Okay, this is a real motivation. You say, why should I compute something which ultimately I am going to throw away? So to answer this, there is this polyphase filtering which effectively use this fact that you only compute what is required. If you think of this in terms of hardware, or remember, let's say here the sampling is at 360 megahertz, 360 mega samples, and for example here you intend to throw away 36, you want to decimate it by 36, so here the sampling rate will only be what, 100 megahertz or 10 megahertz, 10 megahertz. How many samples are there? 10 mega samples every second. Okay, if you compute this filter at this rate, this is the input data rate, you need to implement this entire filter to cater for 360 mega samples per second. At this point you will be computing 360 mega samples per second. So whatever hardware you have needs to work fast enough to give you this rate, and it is only here where you throw away these many samples to get to this rate. Now people have tried to come up with an architecture where this whole thing should be replaced by a design which instead of working at 360 megahertz should work at 10 megahertz. Okay, so effectively make a design, because this is really what the output rate is. So you want all your filters, the convolution, to happen at this rate and not at this rate. Though the input data is coming at this rate, but you want your design to work at this rate. Okay, and similarly in interpolation, what you do? Same is the case in interpolation. That interpolation, first you insert zeros. Okay, once you have all these zeros, so you have this value, then you have zeros, then you have this value, then you have zeros, then you have this value. So you are convolving this signal with a sink, right? So no problem, you are convolving it with a sink, which is something like this. So if you convolve this by this, you are multiplying so many zeros, you are multiplying non-zero with so many zeros. What do you get out of that? A zero multiplied anything is zero. So you are unnecessarily multiplying by so many zeros, whereas you know that these zeros are not going to contribute anything in your convolution. So you really don't want to do this. Though you want the same effect, the effect should be same, that as if you are inserting zeros and then convolving it with a low pass filter, but you never ever want to add so many zeros in your signal, actually going and adding signals, increasing the sampling rate, then convolving it with the signal, and then producing the samples. You don't want to do that. Why? Because if you do this, your sampling, the filter need to operate at a very high rate, at the newer sampling rate. Though mostly you are multiplying by 0. So this is the motivation of polyphase filters, that somehow you figure out a way to run the interpolation and decimation filter at a slower rate. So these are called polyphase filters, and they are used to implement decimation, which is called downsampling, and interpolation, which is called upsampling. So they are used to do upsampling and downsampling, and we have already covered that why you ever want to change the sampling rate. I'll not get into this. So downsampling is by an integer factor requires to throw away. In M, just throw away, out of M, throw away, just keep one and throw away rest of the samples. And this, we have already seen this slide. The effect is that it is stretch of the spectrum. So, and this is what we need to, this whole operation we need to simplify that. First you pass it through a low pass filter and then you throw away samples. So these are the things which you intend to simplify, and we have seen this slide already. And this is the operation after you do throwing away of samples. You get, after you pass it through a filter, then you throw away samples, then you get this. And this is polyphase architecture. It says that if you want to do this, and we'll find a mathematical reasoning for it, primarily you design a low pass filter. As I showed you in MATLAB, you say FIR1 pi over M filter. So you design a pi over M filter. Once you have this filter, okay, the polyphase decomposition requires you to decompose this filter into M filters. And we'll see why we are doing this. For example, this is my H of N, and these are the H of N. These are the different samples of my decimation filter, which is designed by using MATLAB command FIR1. Okay. Now I decompose it into M filters. How I do this? I give first sample to this filter, second sample to the second filter, the third sample to the third filter, fourth sample to the fourth filter, then I come back. Again give this sample to the first filter, this second to second, third. So I distribute all the samples in the impulse response to 4 if I am decimating it by 4. If I am decimating it by 2, I split it up into 2. If I am decimating it by 36, I split it up into 36. Right? This is the first operation I do, and this operation is equivalent to saying that H of N is in fact Ek of N, which is equal to H and M plus K. Means that M is the decimation factor. So I am saying, okay, H, N, let's say M is 4 plus K. Okay, so Ek of N. So let's say what is E0 of N. This is the first filter. E0 of N is H4N, that is. So put N is equal to 0. First sample is H of 0. Then put N is equal to 1. The second sample is H of 4. The third sample is H of 8. So the first filter will get the 0th sample, the 4th sample, the 8th sample, the 12th sample, the 16th sample. This is your E0 of N. Similarly, E1 of N will get H 4N plus 1. So it will get the first sample, the 5th sample, the 9th sample, the 13th sample, the 17th sample. Similarly, E2 of N will get two, 6, 10, 14, 18, and similarly 3, 7, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is the mathematical equation which helps you to disintegrate the filter. So you design a filter, you disintegrate it into 4 polyphase filters. These are called polyphase filters. Then if you do this, then actually implementing a filter means that, or let's say if I have this filter, for example, let's take a very simple example. Let's say I have 1, 2, 3. These are the coefficients. 4, and let's say only 2. 1, 2, 3, 4 are the coefficients, and this is my h of n. Okay, if this is my h of n, what is my E naught of n? 1 and 3. What is my E1 of n? 1 and 4. Okay, what is the Z transform of this? H of Z is equal to 1 plus 2 Z inverse plus 3Z minus 2 plus 4Z minus 3. So this is the Z transform. I can rewrite it because this is my E naught. If this is my E naught of n, then what is my Z transform here? 1 plus 3Z inverse. So this is my E naught of Z. What is my Z transform here? 1 plus 4Z inverse. This is my E1 of Z. Okay, now I rewrite it like this. It is 1 plus 3Z minus 2 plus 2Z minus 1 plus 4Z minus 3. I really want to write h of Z in terms of E naught of Z and E1 of Z. Can I do that? Yes. How? I really, looking at this, I know my h of Z is in fact equal to E naught of Z square plus Z inverse E1 of Z square. And you can check. I am saying if you say E naught of Z square, Z will be replaced by Z square. It will be 1 plus 3Z minus 2. It is 1 plus 3Z minus 2. So it is E naught of Z square. Okay. Then if I take Z inverse out from here, inside you will have 2 plus. What is 2 plus 4Z minus 2? It is 1, sorry, this is 2 and 4. It is really E1Z square. Right? This expression 2 plus Z minus 2 is E1Z square, E1Z inverse. So even if I want to do it, if I want to make 3 of these, m is equal to 3, there will be E naught, E1, E2, everywhere I'll have Z cube, Z cube, Z cube, here I'll have Z, no, Z minus 1, Z minus 2. So to generalize h of Z can be written as k of these, so many of these filter, ek Z minus m. So this is the polyphase decomposition formula, that in Z transform and h of Z can be broken into m EZs. Okay, so and very simple to get to this, write Z transform of h of Z. Then just, if it is decimation by 2, collect this and this, this and this. If it is by 3, collect every third. If it is by 4, collect every fourth, and rewrite it like this, and then do this maths here, and you will find out always you end up having this expression. This is the polyphase decomposition expression. We'll see a graphical view of this expression, and then any h of Z can be broken into number of parallel filters, whether you, so these are the filters, any h of Z, no decimation, no interpolation. It is saying that a filter, one filter can be broken into m linear filters. H of Z, any h of Z, no matter what, usually the FIR, any h of Z can be, if you want to, break into so many parallel, so that once you add these together you get h of Z. Okay, and what have you done? That h of Z, you write h of Z expression, put first sample here, second here, third here, then go back. So it will be all these filters, Z minus 1, Z minus 2, Z minus m plus 1. So if you do this, the first filter will be having Z's power of m, obviously. This will also be having, if you take z minus 1 out, all these will be in terms of powers of m. If you take 2z minus 2 out, all these will be in powers of m. So this is what you get. Okay? This is a polyphase decomposition of any filter, if you want to do it. And let's find out the reasons. Why would you do this? Now z inverse means what? A delay. Z minus 2 is what? 2 delays. That if x of n is here, x of n minus 1 is here. If x of n is here, x of n minus 2 is here. What if I move this here? And how much do I have to move here? Z inverse. A z inverse, a z inverse, a z inverse. Because if I move this z inverse here, then I need not to have z minus 2 here. Only z minus 1. Everywhere I will have z minus 1. So means the current sample goes here, the previous sample here, the previous to previous here, the previous to previous to here. So these samples will be like this. So this is what you do. Okay, so these are equivalent expression. I am trying to come up a mathematical reasoning of computing only what is required. Means that I will not throw away sample. I will make an architecture which will run at a slower clock and which will only compute what is required, not computing the samples which we ultimately throw away seamlessly. So it will be that you are not intentionally doing anything. The architecture will automatically takes care of the throwing away of samples. So we know this is z inverse, z inverse, z inverse, z inverse, e naught zm, e1 zm, e2 zm, and e m minus 1 zm. So this is what you have. Okay ji? So this is really, if I, in time domain, if I want to make this, I would say, let's say m is equal to 3. Okay, let's say my filter coefficients are 1, 1, minus 1, 2, 1, 3, 1, 0, 2, for example. Okay, then I say, okay, this is this filter. I can break it down. I need to do m is equal to 3. So what do? I keep this one, first one here, then bring this one here, minus 1 here, and I still want it mathematically equal to this. Okay, so once I add all h of n, I must get this. So that's why I am writing it like this. Okay, so where do I write 2? So here 0, here 0, then I write 2. Okay, here 0, here 0, then I write 1. Okay, here 0, then I write 3. Here 0, then I write 1. Let's put something else here, 5. So here 0, I write 5. Here 0, I write 2. So I put 0, 0, 0. I do 0, 0, 0, 0, 0, 0. So I can really break this impulse response into 3 impulse responses: H0, H1, H2. Once I add all these, what will happen? I get this. So I know that this is equal to these 3 parallel, and we have learned this in chapter 2 that if systems are in parallel, their effective impulse response is the sum of all the impulse responses. But now there is some problem. What is the problem? If I take a signal, convolve it with this one, and this one. That's why, because parallel system means either you convolve it with this one, or you convolve it with all these impulse responses and then add. What is the problem in these? Extra zeros. I'll be doing a lot extra than what if I just convolve it with this one. So all these zeros, they hurt. Okay, so but though they are equivalent, so this is how they are mathematically written. E naught Zm means that you have zeros. This 0 is not there, sorry. So let's start from here. So E naught Zm is this. Z inverse E1 Zm is this. Z inverse means first you need to put a 0 and then this. Z minus 2 E2 Zm is this. You need to put 2 zeros and then this. So if you take z transform of this, you have 1 plus 2z minus 3 plus z minus 6. So it will always come in powers of m. Okay. So these are two equivalent representation of polyphase decomposition. Now comes that now I put the decimator. I want to pass it through this filter, which is a low pass filter, and then I want to throw away samples. And somehow I want these two to be done in one step where I don't throw away samples. Okay, so I know that h of z can be written like this. Okay, so I, instead of writing h of z, I write this whole thing, and I then say, okay, I'll do this. I add all the samples coming from the output of these three filters, and then I throw away samples. Now I'm doing a mathematical trick. I say, perhaps instead of first adding then throwing away samples, I can bring it inside, and I throw away samples at the output of all these filters. Okay, and then I add. Both are equivalent. Ji, change. Okay, so now I say, okay, if I'm adding and then throwing away sample, why should not I take it on in all these branches, throw away samples, and then add? So I can do this. Obviously, it's like this. Okay, this is fine. Now is the trick which is played, which says really the throwing away of samples here is equivalent to throwing away of zeros here. That if you compute and you are throwing away every so many samples, if you bring this on this side, it will eat up this m. Like once you are inputting to this system, then you throw away samples and then pass it through a filter where there are no zeros, and you can easily check this. Make this an input stream, pass it through this filter. Okay, compute output. Then what you do is, instead of, and then you throw away samples. Now instead of doing that, you remove these zeros. Okay, get the input, throw away samples, and pass it through this filter. Both will be same. You'll get the same answer. So these are called noble identities, and the noble identities is primarily the identities which are used in polyphase filter. This is the identity which helps you to reduce the computation, and the noble identity says if there is a decimation, okay, you can take this decimation on this side of the filter and it will eat up this m. So conceptually what is happening here is that if you have a lot of zeros, after every sample you have m minus 1 0 sample, m minus 1 zeros, you are bringing an input, convolving it with this, then throwing away samples. You basically take the input, throw away samples, and then pass it through a filter without zeros. So both at output of both the system, you'll get the same output. Right? No, x of n is any signal, a time domain signal. No, this is a digital signal. Okay? It's a digital signal. So it has already been band limited, you have sampled it. It is basically, we are saying, if you are in a situation where your filter has zeros, periodic zeros, a stream of zeros, and you are decimating, then you can play this trick. Okay, and how this trick helps is that now if I bring these m on this side, what will happen? It will eat up this m, right? So it will eat up all these zeros, which is good for me, and this will come here. Now so I do this, I get this. Okay, now think about this. It is saying if I have first sample, 0 sample, I bring the 0 sample here, let's say m is equal to 4, then I am not going to bring sample number 1 because I need to throw away sample number 1, I throw away sample number 2, I throw away sample number 3, I bring sample number 4. I bring sample number 4. Here is a delay. So once I bring 0, I need to have 1, for example, a delayed sample. If I started from 4, let's say, if I have 4 here, I will have 3 here, 2 here, 1 here, and 0 here. For example, I should start from 3 in fact. Sample 3, sample 2, sample 1, and sample 0, right? This is how it will work. Because this is a delay, the previous sample a delay, previous to previous sample a delay, previous to previous to previous sample. So 1, 2, 3, 4 branches. Okay. Then if sample 0 is here, then sample 4, here I should get sample 5 because I am throwing away so many samples. Then it will counter sample 6 and sample 7, and this 8, 9, 10 and 11. So what is this? It is a switch. This is a switch which is running at a higher rate. It gives first sample here, second sample, third sample, fourth sample, and then you run this filter, which is 4 times slower clock rate, because first you distribute, then you compute, then you again distribute, then you compute, and every 4 samples you compute 1 sample at the output, because this is a filter. So you give 4 samples, you get 4 out, add them up together and produce 1. So for every 4 samples you produce 1 sample. 4 samples, this is decimation, and the filtering is automatically happening here. So basically you are implementing a filter, but the data is this. You are implementing this filter, data is this. So all these filters are in parallel, working at a slower rate. And the benefit of the polyphase decomposition is that all the filters are working at a slow rate. Only thing which is working at a fast rate is your switch, which is distributing samples.
So if this delay is giving 4 samples every time, why do we need this M then? What is this M doing?
No, I'm saying effectively this M is doing this. M is doing this. Basically this M is saying that I'll keep 0 G. I'll keep 0, I'll throw away 1, 2, 3, then I'll keep 4. I'll throw away 5, 6, 7, I'll keep 8. So this is what the M is doing. 1, 5, 9, this M is doing this. The delay is doing this. It'll keep 0, 1, 2 and 3, but then it will throw away rest of the sample. So basically we replace this whole thing with a switch. A switch which says first give it to this, then to this, then to this, then to this. Okay, so the switch is working at a fast clock rate. It get a sample, give it to this one, this one, this one, this one, and here you have a filter without zeros, a filter without zeros, a filter without zeros, a filter without zeros. Here you put an E0 of n filter, E1 of n filter, E2 of n filter, and E3 of n filter. You get an output and you add all the outputs together to produce one output. Okay, so this is what is happening. A switch is working at a fast rate. All these filters in parallel are working at slower rate, but they are doing decimation. You are not throwing away anything. Automatically that has been taken care of. So this is the polyphase decomposition. I'll show you the MATLAB code for the decomposition, and just to show the equivalency of in MATLAB. So here is the, again, very trivial to implement. There's really nothing in it. You, for example, I'm sorry, I'm using L, I should have used M, but it means decimation by 2. Let's say I want to design a filter in MATLAB. Pi is omitted, it's normalized axis. So once you say pi over L, you only say 1 over L, 1 over M. So this is the cutoff frequency of the decimation filter, pi over 2 filter. So I design a length 40 filter using FIR1 command. This is H. Now this is the polyphase decomposition. I keep first sample here, second goes to this one, 1, 2, 3, 4. So 1 colon 2 colon length, and 2 colon, you can also put end, I'll work equivalently well. So P0, P1. So these are the 2 polyphase filters. So one filter is broken down into 2 filters. Okay, now there are two ways. One is, even in MATLAB there are two ways. One is, so here I am plotting H, P0, P1. One is you convolve X with H, means you get the output and then you throw away samples. Okay, then you throw away samples. Here I am throwing away first sample, keeping the second one, just to show you the equivalency of the two. This is one way, but you are doing a lot more computation. Even MATLAB is doing a lot more computation, because you compute and then you throw away samples. The second is that you ask MATLAB, now you need to, so these are all plots here. This is the switch. You give first sample to x1, then x2, x3, x4, x5. So you split the input into two parts. And this is the switch, 0, 1, 2, 3, 4, 5, 6, 7. So you split it into two streams, x0 and x1. So first sample goes down and the second sample goes up. So these are the input. You split these inputs into two, and then what you do? Pass it through both filters. x0 from P0, x1 through P1. Okay, and then add them together. Because MATLAB has this range which you need to make sure both vectors should have same length, but once you are throwing away sample, one may get more than the other. So I'm just making sure that I'm using the minimum, and that is being used to get both the signals. Then add them together, you get this. So this will be same as the above one, but you are doing a lot less computation. Almost half the amount of computation is done here. If decimation factor is bigger, then obviously you save more. So this is a technique which should be used if you are doing decimation, that you always implement polyphase decomposition. And here is, let me run this code. So this is the original filter, and it is split into two filters. First sample goes to this one, second to this one, third, fourth, fifth, sixth. So out of these 40 sample, 20 goes to this one and 20 goes. So this is the polyphase decomposition. You design a filter for decimation, and you do this, and then do the same for the input samples. And this is what is that filter. Once you apply the filter, you clean up the spectrum, and now you can do the decimation, and that decimation is achieved without throwing away of samples. So, and you do the same with this input signal, this X. So you give first sample to this one, second to this one. So this is what is done. So you give sample like this. So out of so many samples, 1400, you have 7000 to this one and 7000. I pass through P0 and pass through P1, and then add them together to get the output. So this is what is done here, and this I am showing same output. This is where you pass it through filter, then throw away samples. This is you never throw away any sample, right? And this is by polyphase decomposition, you take care of throwing away of samples. Both are same signals. So just you do better than this. And this is the decimation version. Same. Okay. So precisely same trick is played. So this is very interesting. I have been telling people that should we use IAR or FIR for the low pass filtering? Answer is no. Using an IAR filter in this case has an obvious shortcoming. We cannot take advantage of the fact that we only have to compute every nth output, since previous output are required, because a throwing away sample concept cannot work for IAR. Why? Because once you write an IAR filter equation, you need yn minus 1, you need yn minus 2, you need yn minus 3. So I have always been showing this. And then a PhD student came to me and I thought about it. I thought that perhaps you can find out a way to rewrite the difference equation in a manner that there is no yn minus 1, there is no yn minus 2. Okay? I thought about this, and then I did this on a paper. I thought perhaps you can do it. If you can do it, it is a PhD thesis, right? And it took us like 3 hours to make a PhD thesis, really. So we really came up with an expression where you can in fact use an IR filter in polyphase decomposition. So we wrote a paper that paper is accepted in a journal. So he has in fact the student has written his PhD thesis as well. But it was this slide which motivated me to think about it, and perhaps I'll show you. I have a copy of the paper. But primarily what we did, that somehow we wrote the IIR equation in a manner where you only require the mth whole sample. There is recursion, but the equation is written there where y of n only depends upon y of n minus m, y of n minus 2m. So if somehow, it is very difficult to write it in this manner, okay, not very simple, straightforward nahi hai. If somehow I can write it like this, okay, it means I compute y of n, then I need not to compute n minus 1, n minus 2, I can reuse this. So if I can do that, I need not to compute also. I can use IR filter, which are more effective filters. We know that IR filters are more effective. I can use an IR filter to do decimation. So this was done, and so this slide is no more valid. So upsampling is where you upsample by L by inserting zeros. You say so many zeros and then sample so many zeros and then sample, and the same thing comes that why we are multiplying with so many zeros, why you insert zeros and then you do all of that. So zeros, inserting zeros and then passing it through a filter which requires many multiplications, right? These are the slides which we have already seen, and we know this is what happens if you insert zeros. You get, if L is equal to 2, you get 1 extra copy. If L is equal to 3, you get 2 extra copies, and the filter will primarily remove the extra copies, and this is what the upsampling is. So the filter will remove the extra copies. Acha. So we have already done this. Now let's go back to the interpolation. Interpolation, first you insert zeros, okay, and then you pass it through a filter. So we already know the polyphase decomposition of H of Z, which is E naught Z raised to the power M or L is just a factor. You can write Z inverse on this side or this side, it does not matter, because you can always change the position of this. It will not, because both are LTI system, this is just a delay. So instead of writing Z minus 2, Z minus 3, I am writing them on this side. And the interpolation is here. So you insert zeros, then feed it to all these filters with zeros in them, okay, then delay them in this fashion, then add them to produce y of n. This is what it says. Again we use to bring it in, so inserting zeros here or inserting zeros in all the branches are equivalent, okay. So we do that. So inserting L, so you have here. Then we use a noble identity, which is this. This is the noble identity. It says that if you bring this on this side, it will eat up this L. That was reverse of it. Okay, if you have an interpolation and then a filter with several zeros, you change their location, so you pass it through a filter without zeros and then you insert zeros. Okay, so this is what you apply here. So if you apply here, these will eat up all these z raised to the power L, and you have inserting zeros coming here. Okay, now look at this. If you have this expression, this, okay, now what it says? It says don't insert zeros, get the signal, do the polyphase decomposition, okay, and then pass the signal through these filters. And really what this means, inserting zeros, let's say inserting 4 zeros, inserting 4 zeros and a delay, inserting 4 zeros and 2 delays, it is like a switch. Only it says that because you have a sample, then you have 4 zeros in this case, and this sample will be delayed by 1. So this sample will come here, then again 4 zeros. This sample will come after 2 sample. This sample will come here, then 4 zeros. So it is like a switch that you input one sample, pass it through all these filters, then pick. So out of 1 produce 4. One sample comes in, you produce 4 samples, then use a switch to pick this first, then this, then this, then this. After one, so for every one sample you produce 4 samples, and there are no zeros in the system. This is just x of n. The filter is important, is that filters are working at a slower rate, because this is the rate at which you are getting the samples, you are filtering them. Only this switch is working at a high rate, because this switch needs to pick this 4, and again 4, again all these filters compute and you pick 4. Okay, so this is the polyphase decomposition of a filter for interpolation. To summarize, this is perhaps the last slide. To summarize, whenever you want to decimate or interpolate, and you do this a lot. You do this a lot in all signal processing and image and video processing. It is better to decompose your filter to polyphase filters. So it is always better to decompose a filter into polyphase filter, and that is very simple. Design a filter and then distribute that to M filters, and for decimation you also do the same with the input signal. Pass it through so many filters, add the samples together to get an output. And for interpolation, you take the same input, pass it through all these filters, and then pick all these samples together, you get the interpolation. So you can do both decimation and interpolation using, in this case, FIR filters and the polyphase decomposition. And this is what is usually done. There is just one small topic which says, what if you want to change the sampling rate by a non-integer factor? Let's say I want to change the sampling rate fs as 2 by 3 fs, the new sampling rate fs dash to be 2 by 3 fs. 2 fs means I need to increase the sampling rate by 2, and 1 by 3 means I need to decrease the sampling rate by 3. So the good way to do this is that you always increase, because while you are increasing the sampling rate, you don't lose any information. So always you increase the sampling rate and then decrease the sampling rate by 3. Okay, so means you need to do this. First you increase the sampling rate by 2, then you decrease the sampling rate by 3. We know whenever you are upsampling, you insert zeros and then pass it through a filter. So this requires us to increase by 2, pass it through a filter with cutoff frequency pi by 2 minus pi by 2 and gain 2. This is what interpolation requires us to do. Insert zeros, pass it through a filter. Then the decimation requires us to first pass it through a filter with cutoff frequency. In this case, what will be the cutoff frequency? Pi by 3. And then throw away samples. This. Okay. But remember that these two filters can be put in as just one filter, because a low pass. So find out the maximum of these two, pi by 2 and pi by 3. A maximum of this will be minimum of pi over this. So you find maximum of L over M, so pi over K. So in this case you put pi by 3 filter with gain 2. So you can really put just one filter, pi by 3 filter with gain 2. So you interpolate Okay, this is by non-integer factor. And I'm not sure if you can figure out an IR filter for this as well. But this is where you have to first insert zeros, pass it through a filter, and then you throw away samples. Though I know there are polyphase decomposition for this as well, very complex polyphase decompositions, but no straightforward way of doing it. Okay, because you are first inserting zeros, passing it through a filter, then you are throwing away samples. This is if you intend to change the sampling rate by non-integer factor, but it's a rational factor. And there are ways, if you cannot write something as 2/3, irrational, there are ways of doing it as well. It's not covered here, but there are ways. Then you use some other form of interpolation to change the sampling rate by an irrational factor. But this slide shows that you can change the sampling rate by a non-integer factor like this. Okay? And this is pretty much this is the slide I want to cover. These are just a few research papers to show the band pass sampling. I'll give you these slides if some of you may be interested in just going through these. These are band pass sampling and research in polyphase. It's a pretty recent paper talking about digital receivers and transmitters using polyphase filter banks and wireless communication. So pretty much covered this. Let me see if I can show you the ठीक है जी, थैंक यू वेरी मच।